start with following the previous speakers, starting with Alexei. First, thanks to the organizers of this nice workshop, which is very nice. And second, saying these words that I would try to say something elementary, concentrating on this, and outside of the main direction, like many people already mentioned, but I think the reason is very simple. Since we have already this 14th workshop, so the science develops, and it's very hard to follow some narrow stream, which was probably your idea originally, right? To have this on EGT and stuff related like that. On the other hand, we have some kind of quasi-periodicity in science, if you wish. And it looks like that, well, the topic actually I will try to say was a sort of origin, maybe, of all this science, previously even to strictly formulated geometric relations for gauge theory, and it sort of started from the area of two-dimensional quantum gravity. And in a sense, what I want to say, I want to maybe, well, define one of the main objects in this science, this Krichever or quasi-classical tau function. Well, by many reasons. So there are two historical reasons. One of them is that this science was intensively developed also here in CISA, and even before this explosion of this activity due to Julia and Alessandra, so by Boris Dubrovin and people around him, it's very close objects. And sometimes, well, I found myself very old here, that just in the sense that young people use more and more some different language, and in particular, well, these main objects from this science, they are now referred to usually as to certain, well, things like topological recursion, which is definitely not true. And then I said so that I will try to start from some origin, from some really elementary things, this definition, because many people, when studying two-dimensional quantum gravity matrix models, they came to this object, but Igor Krichever was that one who managed to define it in pure algebraic geometric way, if you wish, and define this sort of integrability as the simplest possible integrability, just coming from Riemann bilinear identities. And then there were many applications, as I said, to matrix models, topological strings, Seiberg-Witten theory, coming back and forth. And then, well, I will concentrate on one of the most important objects from this science, this residue formula, which was again defined originally in 90s by Igor and maybe also by other people. But so Igor had strict definition and derivation of this formula, though it was never written actually. And maybe that's why I want to mention it especially, and then say some simple statement about its relation with WDVV equations, also intensively studied here, and then turn to this modern applications concerning this two-dimensional quantum gravity. Again, maybe starting from some preliminary old ideas, but what will be my point in the end is that this science came back here, and there is a direct relation of the Krichever tau function with the known from absolutely different context, Verlinde formula for the fusion algebra and modular S matrices, and which even now, as maybe people who followed the talks, this string and string math conferences it has some non-algebraic generalization. So, well, again, excuse me for this elementary things, it's just some notation. So we have some compact-oriented Riemann surface or complex curve with only topological characteristic is genus. And so the dimension of the first homologous is 2G, so it means that one can choose in this first homology some symplectic basis of A and B cycles, which is always used in this science with this intersection form. And dual basis in cohomologies can be given in terms of holomorphic differentials, and usually, or first kind abelian differentials, and usually they are taken just to be normalized to the A cycles. And then the B cycles give the very well known everyone the period matrix. And so what are these Riemann linear identities? Some identities for abelian differentials, which then lie to the core of integrability properties. So first, just this simple, the simplest example is for the holomorphic differentials. You just take the wedge product, and which is 0, so the integral is 0, and then you just cut the Riemann surface into 4G and apply the Stokes formula. Then from this Stokes formula, it gives simply an integral over this boundary of this foregon. And if you look carefully at the integral of this boundary, how they appear here, you just see that this Stokes formula gives some relation, so that this integral over two-dimensional surface, which is 0, is given by some bilinear combination of line integrals coming from these different segments of this boundary. And again, if you look even more carefully, it would just the result is antisymmetrized part of the period matrix. So since it is 0, the period matrix is symmetric. And that can be obviously generalized to some other abelian differentials, which are used in this science. So the second kind abelian differentials have higher order poles at some given point, say, which is denoted here P0, and they depend on the choice of the local coordinate. And usually in KP theory and what follows from that, we choose this local coordinate, well, in a way that the main part of this abelian differential is simply given by the highest possible order terms plus something regular. And since they are defined up to the addition of holomorphic differentials, they can be normalized in some way, and usual normalization is for the vanishing A periods. The third kind of abelian differentials, or dipole differentials, which are also intensively used in total theory, can be even defined in terms of the prime form, just the d of logarithm of the ratio of prime forms with 2 points p plus and p minus, where they correspondingly have the first order poles. So here the choice of the local coordinate is not so much essential, and at such definition they're just normalized to 0. So it's not like necessary to write it, it's from any textbook. Yeah. And again, applying the same elementary logic to the wedge product of holomorphic, say, and the third kind of abelian differential, you again first apply the Stokes formula, which gives you, as we saw before, this kind of contribution. But now, due to the poles, so also the integral, and that I will use in what follows, the integral over this cut surface can be shrinked. To this integral, you get a contribution of the residues at these poles, which give you these two residues. They give you just the line integral between these two poles of the holomorphic differential. And so, in such a way, you can repeat this logic and get many similar formulas. And the basic idea that this Riemann bilinear relation give you some identities which can be used for introducing the quantity of some, which has a relation to integrable systems. And so, to define it, well, I first need to introduce on a complex curve some extra structure. And so this extra structure is this Krichever data. Usually it's a pair of meromorphic differentials, dx and dy, with fixed periods. By fixed, I mean that these are zeros or some numbers which do not depend on the moduli of the curve. It's very hard to be strict here, so I just give a general picture, because in many cases it needs some extra definition. But the idea that this, when you introduce these two such differentials, then and impose this condition, each of them is roughly G, where G is the genus of the curve conditions on the moduli space, and effectively it reduces by 2G plus minus something. So it reduces the family, the generic family of the curve, to the G parametric family of the curve. And this is the holomorphic, then analytic generalization of the Liouville theorem, where you have this G-dimensional family of the curves, and you can choose G-independent functions, which are on moduli space, which are the values of Hamiltonians or action variables, while the coordinates of Jacobian give you complexification of the Liouville torus. And so in such a way, you naturally come to some integrable system. So, and now the definition. So to define the tau function, I will start from some degenerate example, which has another name prepotential. And for that, you need G-parametric family of these Riemann surfaces with Krichever data, or you can say that it's endowed with a generating differential and connection on moduli space, how you differentiate these functions, so how you compare these functions on two different Riemann surfaces. And so the requirement is that the variation with respect to such connection is holomorphic, and the prepotential then is defined in the simple following way. So the variables are, you take the homology basis, divide it into A and B cycles, and then one set of periods is gives you the variables, and another set of periods gives you just the gradients of the function, which is the prepotential or logarithm of the tau function. And so this is some local definition actually on modular or even Teichmuller space. But the only thing you need, and the only thing you need to check, that this definition is consistent. And once you've chosen this connection, you can easily check that it is consistent, that indeed these many variables are gradients of a single function, because the cross derivatives due to this condition gives you the period matrix, and we just saw that the period matrix is symmetric from Riemann bilinear identities. It means that dAd over dAd alpha over dA beta is a symmetric matrix, and this indeed can be integrated up to a functions. So, questions up to now? Or indeed everything is known? You will ask me later. Okay. Huh? I don't want to show my secret, so I will ask you later. Okay. Constant shift of what? Of this function itself? Yes. Well, that's usual. No, just I'll answer then to your naive question. So it's as usual. You see, tau functions. Well, generally, by this word, you can now name many different things, like tau functions appearing in this theory of KP to the hierarchies, isomonodromic tau functions, whatever. They're usually defined always up to adding of something. Constant is the minimum. Well, constant means really nothing. It's, for example, if you remember this talk of Oleg, he also mentioned that his tau function is defined up to certain normalization constant, which can be, well, very important because it depends on some particular data. Here it's also as well, but constant is absolutely minimal requirement. Yeah, the only thing which is important here is that since these are period variables, they are good flat coordinates like people have, because they have a linear structure of them. And that is used intensively everywhere.
If you take your previous slide,
yes,
Krichever data
yes,
define an integrable system.
Yes.
Then you go to the next slide.
Yes.
And you say that Krichever tau function.
Yeah. But this is not tau function of that integrable system.
Anyway, you take Zyberg-Witten, you will have this prepotential defining in the similar way. Take it, I'm wrong. Am I wrong? That it is not a particular case of Krichever tau.
Yes, it is.
Because it's Krichever.
Just take his paper and look.
No, I mean, I just want to any integrable system, you will have similar procedure of generating quantum appearance. And,
in principle, yes. So in principle, what is the answer maybe to your question is that it's not kind of a classification or a theory, or a theory, but it is natural to consider these quasi-classical Krichever tau functions for the family of curves which correspond to some classical integrable systems.
My question is very simple. You say the particular case of Krichever tau function because your integrable system is Krichever date integrable system. If you take another integrable system, you will define another.
Yes, that's true.
Yes?
Yes, that's true. Well, for example, I will probably have to skip this because it's really some old stuff, but this is this very well-known equation for the complex spectral curve of a fine Toda. And this is just one of the main examples because it arose in the context of Zyberg-Witten theory. These curves correspond to pure gauge theories, but here indeed, so you have two meromorphic differentials. One is just differential of a hyperelliptic coordinate whose all periods are zero, another third kind abelian differentials whose periods are integers, because it's d of logarithm. And then the question, why just I put this old example here, is how to define this connection. And so one can pronounce many clever words, but the point is that you just choose some covariantly constant section for this connection on two different curves. So while so these UKs are parameters of embedding of this curve into C times C star. And when you move them, so shift them, you change the complex structure. And so you move along in vicinity of some point in modular space. And so you just say that one of the functions, one of these abelian integrals, is covariantly constant. Then you take a derivative of another one, just varying this equation, and you can check in this way. This is a simple exercise that variation of this generating differential is indeed holomorphic, because what is written here is generic holomorphic differential on such curve. And that's all you need. So, but that was, well, not actually the first one, but one of the most simple examples from the point of view of complex geometry. Some other ones are, which are coming literally from KP theory, are slightly more complicated. And in order, for example, these sort of extra formulas, they correspond to second kind abelian differentials, and they indeed come from KP theory. In the case of in the case of rational curves, this is literally dispersion as KP, and basically they're the same. So the period integrals, they change to residues of the differential multiplied by some power of local coordinate. So here this choice of local coordinates is very essential. And then the gradients are given by different kind of residues of the same objects. And consistent condition, again, if you take a second derivative, it would be such residue. And due to particular clever choice of local coordinate, as I said, this differential of this omega n is just, so this is, it's inverse local coordinate here. So, because it's typical in KP to normalize it at this point to infinity, not to 0. And just taking, the main part is given by just simple power of this local coordinate. It gives rise to symmetricity of this expression, and this symmetricity is a particular case of a Riemann bilinear identity, however, remains the same. But application is a bit different. And so that's basically what I wanted to say in the definitions. So the definitions follow from Riemann bilinear identities. They can be done for any set of abelian differentials. So, I would maybe, for some generality, denote them as DH, which can be first, second, or third kind, or actually some differentials with jumps, which also Igor considered originally in his paper. But for them, well, at least the clear applications are not yet known. This is the corresponding set of flat times, so the times where here you admit some linear structure. And so, well, there are some non-trivial properties. One of them is so-called PQ duality. Again, that maybe that not the right name, but we'll see how it comes. So it actually means that that there is some symmetry between the meromorphic differentials which coming in this pair of Krichever data. And sometimes it's rather trivial, but sometimes it's rather non-trivial. Say for prepotentials, it simply means that you need to change the covariantly constant section in your logic. But for dispersionless KP, this example on a previous slide, it is indeed some very non-trivial statement for this quasi-classical tau function. And also I will try to demonstrate it in what follows. Because it gives some non-trivial relation for residue formulas. And so, as I just said, this basically is this definition of this quasi-classical tau function is starting point for the topological recursion, and topological recursion is actually an attempt to add extra pieces in perturbative expansion to these formulas. And by some, well, strange reasons, now more people are concentrating to this topological recursion, though, well, in some papers you can sometimes see the statements that all corrections, they are easily defined by this algorithm, except for this main one, except for this f. And from the point of view of physics, it's like you say that you neglect what stays in the exponent and consider only the definition of corrections, which is a bit strange. Okay, so up to now, well, I finished with this part. Any questions?
Should we think about this x and dy in some sense like coordinates on symmetric square?
Well, in some sense, yes, but as I said, it's not always true. So sometimes it changes almost nothing. Like in these corrections to this function, there is some definition of sort of symplectic invariance. These are just actually symmetric with respect to this exchange. But sometimes the main contribution is not symmetric at all. Okay, and so now this one of the main theorems which comes from this definition, that there is a very nice formula for the third derivatives with respect to any set of times. It's very generic. And it just says that the third derivative of this Krichever tau function is given by the following expression, which is a residue over the zeros of one of these differentials in the denominator of such one form, where here, of course, is not a wedge, just a simple product of differentials. So what stays here is one form on a curve. It's very universal. It has some actually string theory ideological origin, because it distinguished the 3-point functions on complex curves among all others. And as I said, so maybe it's instructive to give some idea of a proof, since this proof is not carefully written anywhere. and say, well, the idea is obvious. Yeah, if you need a third derivative, you need to take one derivative of the second. So, for example, in prepotential case, you need to take a derivative of a period matrix. And then again, you use the same trick, just using that there is a particular relation for the differentials and their abelian integrals on cut curve. You can rewrite this derivative as an integral over the whole cut Riemann surfaces of this omega beta, which is a abelian integral of a differential corresponding literally to this cycle. So you have then this formula, and then further you take some manipulation. You just say integrate by part, and then, well, there is some expression, the integral over this boundary of this Fujigong, and you use the fact that this derivative actually acquires some poles, and we'll see now why, and you just contract the contour to the residues of these poles. And the point is that the residues, so this is the definition of this connection. While x is covariantly constant function, this connection, well, it defines everywhere in a very nice way a part of the points where dx is equal to 0, and so the x cannot be considered as a coordinate function on your curve. So at these points, this object requires the pole, and so you can simply compute this integral, like in complex analysis course, by contracting the contour to the set of these poles. So why? Well, it's almost obvious. So when dx is equal to 0, then the local coordinate is square root, say it's some point xa. The local coordinate is square root of x minus xa. And if you take an expansion of this abelian differential in the vicinity of some point and apply this connection differentiated at constant x, you definitely get this guy in the denominator. And that means that you get a pole. Now, how to deal with this pole? You just need to look again at this formula and see that the expansion of the holomorphic differential around this pole would have the similar structure, but here there would be no pole because this pole would be cancelled by the zero of dx. But this particular quantity can be roughly given by the ratio of this derivative and the omega. So then the residue, this residue of this, well, you can simply write in this way. So here is just what is written from combination of this formula, and you make one more similar step in order to rewrite now this derivative of position of this branch point using the expansion of y, and again basically by the same trick. So at the end, you simply by direct computation, you get such formula. So, questions? It's very simple logic, but not necessarily straight. Okay, and well, just as a maybe totally different example, one can, but which would be important for me in what follows, one can consider the so-called topological Landau-Ginzburg theory, where one of these functions from Krichever data is given by a global coordinate on CP1, and another is some polynomial of the global coordinate. Here it's called W. So that's really the dispersionless limit of KP theory for particular solution. So what is written here is the one of the form of dispersionless Lax equations, and then these flat times, which were introduced before, they are given by such simple formula. So now all this formula just comes from application that sigma is now sigma naught, it's just sphere, lambda is some global coordinate on this sphere, and W is another coordinate, and as by local coordinate at infinity, inverse local coordinate of infinity, we take simply, it has their pole of the order of n, and we take one of the nth power of this W to play the role of psi. And so here the application, direct application of formulas which were written before, they're very simple. You can take this derivative. So the first formula is given by, from definition by such expression. Then you take one more derivative and you get some analog, again a symmetric combination, some analog of the degenerate period matrix. And once you get the third derivative, you get this dw d lambda in denominator, and this is reduced to such well-known formula for all studied topological strings, which is probably called the Grothendieck residue or something like that. So pretty simple. And again, one more historic remark about some years ago, very intensively discussed subject of the WDV equations, which in this Landau-Ginzburg theory, they simply follow from the polynomial ring. So you consider the polynomial ring modulo W prime. So in this way, you define the structure constant. This can be done in any basis, but in the basis of flat times, where these phi's, like on a previous slide, correspond to the particularly chosen times, these structure constants can be integrated up to a function. And so the property of this ring, so this is the polynomial, finite dimensional polynomial ring, so that the matrices of the structure constants commute. And once rewritten in terms of the derivative, in terms of the third derivative, here are these 3-point functions, this system turns into the overdetermined system of the differential equations, which can be in the most compact form written in such a way, where these objects are matrices built from the third derivatives of the Krichever tau function. And the point about this widely discussed subject is the following, that once you have the formula for the third derivatives in terms of these residues, then the WDV equations satisfies automatically once the matching conditions hold. So that the number of times in this formula from which you form your matrices corresponds to the number of critical points of the differential dx, taking into account some possible involution. So this is written as an important remark, because usually, say, when you take Landau-Ginzburg example, this is just a trivial statement. It's roughly the Gauss theorem that the number of roots of the polynomial is equal to its degree. But if you go to, say, surfaces of high genus, then the number of zeros of such objects starts to grow linearly with genus. And in order to, sometimes people were amazed that these equations not necessarily happen, though they expected from some different grounds. But the point is that you just need to consider the cases where this is counted carefully. And so the second remark is that upon non-degeneracy, the proof of this statement is obvious. And the third is that constant metric is actually not necessary. And this simply, all these sort of proofs simply follows from a condition like that. You can consider this actually algebraic relation where lambdas are the set of zeros of this dx. If the number of this number of alphas is equal to the number of Latin indices, so then this is a square matrix. And if it is non-degenerate, you can just express the structures constant through this formula, and then you have to check the consistency condition with the in flat times with the third derivatives of the tau function. And this algebra can have a modification, simple modification, if you multiply here by any function of xi, such that it's not vanishing in these points, then the same logic is applicable. And the only thing you have to check that the consistency conditions will now change from the equality that before this bilinear form was the matrix of the third derivatives where one of them was fixed to vacuum state or to unity, and now it is just changed to any linear combination. So basically, yes, absolutely. So it's just this equation, when this vanishes. So at these points you have this finite dimensional. Absolutely. Okay, so, and then I want finally to, well, maybe come back to the origin and to generalize as much as possible this picture for the case of to the minimal gravity, and then maybe this non-minimal. So by minimal gravity, usually people, when speak about, they have in mind some minimal PQ model interacting with a Worldsheet-Liouville gravity. And actually, though it was claimed in the 90s that the correlation functions computed in Worldsheet formalism, in the matrix model formalism coincide, actually nobody checked this, honestly, and it was not even possible to check before Alyosha Zamolodchikov wrote down his famous high-order Liouville equations. And it was already the first years of this millennium. So, but nowadays, many things can be checked, and people found that the relation is in fact very non-trivial. So indeed it exists, but it has not yet, to my mind, checked up to just generic theorem, but more and more example appears in favor of this point of view, physically obvious that two-dimensional gravity is a normalizable theory, and you can compute objects there in many different ways, and you always get the same answer. But so this PQ minimal model, so it comes from original matrix model approach that it can be considered as a particular version of a KP theory, and once you consider the correlators on sphere and the correlators, well, on high Janus Worldsheets, to compute them is a more complicated problem. So actually, for the first, we need just this spherical limit. This is just a so-called dispersionless limit of KP theory, where instead of two operators, Lux and Orlov-Schulman operator, which commute to some constant, you just replace them by functions. And so these become, instead of two differential operators of order P and Q, they become two polynomials of order P and Q. Generally, they satisfy, well, such polynomials, they actually satisfy this sort of condition. And in general, this is a condition for a smooth algebraic curve of genus equal to the number of primaries in minimal model. But here there would be, of course, some particular coefficients since this curve becomes rational. So it is the degenerate curve of such genus. And, for example, here I can easily plot them. And I will give here an example of, here is Yang-Lee case, the model 2, 5, and here this Ising model 3, 4, and you obviously see that here the genus is 2, and here the genus is 3. Right? Is it obvious? Well, you just a bit resolve this. So there is one cycle, another cycle, A and B. And so here also these three intersection points, these are just nodal singularities, which you obtain by reducing the curve.
So this is the singular locus of the curve you showed us, yes?
Yeah. Well,
fantastic. Can you give a reference?
To this? Wolfram mathematics.
No. The equation for genus equal to 3, for example, it's x to 3 minus.
Yeah, well, Ising is not, it's just an example, because what I just said is that any two, if you have polynomials of power P and Q, they satisfy this equation.
No, I mean, for example, f sub ij of Ising.
Okay. Well, that I can give you. Yeah, it's not a problem. Okay. Well, then, as I said, this is solved on sphere in terms of dispersionless KP theory, and actually this is this version well, you can find everywhere, maybe, say, extract from some nice paper of Takasaki and Takebe. Just you write down this generating function, and everything comes from its analytic properties. I won't stay with this much, but indeed it's some simple exercise that say dependence of x over this times follows from the equation that ds at dx equal to 0 is 0. And this is a system of kind of Godot equations at p minus 1 roots of this polynomial. So it's easy to write down from analyticity, and one of the statements from this dispersionless KP, which is also can be used in two-dimensional gravity, is this any Hamiltonian, which is just a derivative of this generating function. And as we already discussed here, it's just correspond to meromorphic differential, having singular part, local coordinate to the power k. This any such Hamiltonian, so just by definition, is a polynomial, since we live on sphere of a variable lambda, which is h1, and that comes to that leads to so-called dispersionless Hirota equations, which say that all second derivatives of these quasi-classical tau functions are expressed in terms of second derivatives where one of the variables is fixed to be 1. So in dispersionless limit, the bilinearity of Hirota equations in KP theory turn into the fact that these are algebraic relations for the second derivatives, and this is one of the examples of them. So now, well, I did not present the formulas you wanted, but they actually comes from, say, these formulas. In Ising case, it's a simple example. When you have these polynomials, from residue formulas, you always have the expressions that flat times are polynomials of these coefficients. So these flat times are coefficient from these polynomials coming from the operators of KP theory. And you cannot always express x's in terms of t, because these are solutions of nonlinear equations, but sometimes you can reproduce some simple formulas, say for these coefficients in particular, for some of them. Or here you can solve this, for example, for x naught, and get the expression which is known long ago as Bulatov-Kazakov equation in gravitational Ising model. Okay, so let me, well, say that nothing can be said in full for generic P and Q, but when one of them is equal to 2 is the second simple example after this Landau-Ginzburg case, where one of them is equal to 1. And for example, if you consider this P equal to KdV reduction, then many formulas become explicit. So this is the string equation coming from this analytic requirement, as I tried to announce. And well, those at least who knows can easily recognize in these formula the original string equation coming from matrix models. And here even the this Krichever theory gives some explicit formula for the quasi-classical tau function in terms of this u variable, which is again coincides with some matrix model formula. And this is all good apart from the fact that it's not enough to compare, and you hit into problems when you start to compare this with the well-sheet gravity. In particular, due to two effects, presence of so-called resonances related with possibility of already nonlinear reparameterization of couplings. So these flat times, these are couplings in 2D gravity theory, but they do not literally correspond to the couplings in the well-sheet framework. And this allows some nonlinear redefinitions, which is a very bad thing from the point of view of KP. And so this resonances is one of the problem, which can be here killed because they're absent if instead of 2 reduction or KdV, you consider 2k plus 1 reduction. And there are also delicate points related to residual formulas, since it may acquire contributions from infinity, and also application of this stuff. And I will now demonstrate what happens here for if only the time when you reduce to the space of variables where only the time corresponding to cosmological constant is non-zero. I especially used it here different letter because in different theories cosmological constant correspond to different flat time. And this is so-called Chebyshev background. Well, Chebyshev background because here this spectral curve equation can be written in the form where you here Tp and Tq are so-called second kind Chebyshev polynomials. And they, due to they have very many nice properties. I don't know even, well, Chebyshev, of course, was solving some totally different problem, but in particular, this equation implies that in terms of a global parameter on P1, they also reparameterize in terms of themselves. And so this curve is degenerate at such conditions because the derivatives of these Chebyshev polynomials of second kind are Chebyshev polynomials of the first kind, proportional to. And for PQ equal to k plus 1, this is just the general hyperelliptic curve where you can easily find all these parameterizations and it corresponds to such picture. And so this Z, they correspond to these degenerate cycles. This is one set of important points. And that was intensively studied by Zyberg with co-authors some time ago. But for us, more important points will be those ones, which I will denote by zeta. These are the critical points of dy. And again, you see from this picture that these are critical points of dy, and the residue formula localizes on these critical points. It can be also localized by a single critical point of dx. Again, you see from the picture that it's here, corresponding to z equals to 0. But it will lead to some, at least unexpected to me, for me, statements. So I will, let me maybe skip all these properties of this Chebyshev algebra. Actually, it follows from two-dimensional conformal field theory, where it was first derived. It has some nice ring structure. It has some non-faithful tachyonic moduli, which, well, it's interesting to play with that, but we come to this only if we need, especially to this nice resolution. And let me directly turn to this residue formula. So, take it on a Chebyshev curve. So, and take, as I said, these two k plus 1 reductions. So, consider it at the points where dy is equal to 0. Then, this is just the sum of the residues at the points where this even Chebyshev polynomial of the first kind equals to 0. And those points can be easily parameterized. These are these zetas, which were on the picture. So you can just take literally this expression and compute all these formulas in terms of trigonometric functions. So trigonometric functions here are rather simple. And so what would you get? You just use the only maybe slightly non-trivial thing is to use, say, this formula to express one more derivative. And then you just get this finite sum. Naively it's 2k, but due to symmetry it has only k terms. And once you substitute zetas here, you obtain such an expression. So this is the sum over sines, which first looked to me like being trivially computed, but it turns out that it's not a trivial one, because it's a Verlinde formula for these 2k plus 1 model. Well, so in certain sense, it's a very trivial statement because that is what it should be. Since this sum is given, so it equals up to certain factors by the coefficients of the fusion algebra, this is, in a sense, the definition of the minimal gravity. So because it depends, and now there are many definitions of different gravity theories, it sort of depends due to possible consolations of zeros and poles in the 3-point functions, say in Liouville theory, at different values of central charge. It just depends on what you do first. And minimal theory is defined in a way that you first use this fusion, and then you couple you couple what you have, this finite dimension of primary fields to gravity. So that is obviously that what should be given here, but it is what I was also amazed by, that it literally comes from the residue formula for the third derivatives. And this is just kind of a reminder, because well, Verlinde formula follows from from the relation of some global quantities like S matrices for the modular transformations of conformal blocks with these coefficients of the fusion algebra. It has this form, and it is actually well known. So generally for PQ, it's already not so simple. It is the matrix which whose square is equals to unity, and this is its explicit expression, which drastically simplifies in the case 2 to k plus 1, and so it gives just this expression with a single sign. And if you substitute it back, you will just see that these are exactly these signs which show up in this formula. Now, what is the point? Well, the point is that first you reproduce what you should physically expect, and you can check that here this energy k are either zeros or unities, if you carefully take into account the sign factors. But another point is that actually this Krichever science gives a non-trivial proof of this formula. Because here, when you can look in a different way. Suppose you want to prove it, and you just consider the result of such expression, and rewrite it in the form of zeros over dy. But then you can move this contour. And in this theory, when you move this contour, so you get two more contributions. So one is the zeros of this dx, and here it's a single point. Remember the picture of the curve. And another is slightly more, well, complicated and generally unexpected residues from infinity. But nevertheless, well, you move this contour, and then one of these residues is computed immediately, and another is computed after some set of relatively simple manipulations. And so this formula for the third derivatives actually gives one more, to my knowledge, proof of this Verlinde formula and some explicit expression, which, well, of course, adds and in a sense it's maybe not so elegant, but a direct one compared to the previously known. And so finally, I just want to say that what was seen recently at these conferences, in the talk of Collier, probably, it was announced that there exists an infinite dimensional analog of this formula, and that is actually an expansion, as I understood, of the Malochikov's formula for the three-point function. So here, instead of in the non-algebraic case, which Igor Krichever didn't like at all, but nevertheless here the same technique is easily applicable. So b squared, which was a rational number in minimum theory, now is just some irrational number, and there is no fusion anymore. But when you look at this formula, so first what you notice that what stays in the denominator, combining, well, naively it looks strange, but combining with this minus factor, it's actually literally the element of S matrix, which would correspond to the unity operator, so where P naught is the momenta for the unity operator. And second, you just see that the same expression comes from this application of residue formula to the Chebyshev curves, but now instead of Chebyshev polynomials for irrational B, you just have only this cosine functions. So anymore, this B squared is some real number. And so this is this non-algebraic curve, which all normal people from algebraic geometry hate. But actually, the formula is given just by the same expression. And you can count, so here is dx dy in the denominator. You just again count that double derivative of x gives you this sign factor. And the first derivative of y in the critical point gives you this sign. And so the rest comes from the edification. Again, generalizes the Chebyshev formula for the value of Hamiltonian's phi. So, well, that's what I wanted to say. And so that we, in a sense, now this interest to two-dimensional gravity came back, and so it was sort of reappeared, and people consider now different models coming beyond this minimal gravity, but that approach based on simple algebraic, two-dimensional algebraic, one-dimensional complex algebraic geometry related with this tau function introduced by Krichever, so it can be maybe also developed here. So I think I have to finish, and thank you for your attention.
So I have a basic question. You're talking about supersymmetric minimal models.
No.
How come they have Landau-Ginzburg description?
Well, Landau-Ginzburg are unequal to supersymmetric, right? You see, in this theory, there are many different approaches which gives always the same. So the point is that, say, if you consider this generic PQ minimal model, they appeared in just by Belain, Polyakov, and Zamolodchikov in the classification of ordinary two-dimensional conformal theory. But each of them has some extra algebraic structure. Sometimes it is supersymmetric. But, well, there is no general rule how to follow this. So for Landau-Ginzburg, which is in this language is very singular because it's P1, and whenever you have this P1, it's negative central charges, so you have to, well, to use some other definition to work with it. But generally, there is no supersymmetry.
This is what's confusing, because always these beautiful formulas appear supersymmetric.
It's true, but it's two-dimensional gravity. It's very simple science. And here, supersymmetry is not obviously necessary. There's also two-dimensional supergravity. And if you, say, take Zyberg papers, he immediately writes generalization for the supersymmetric case. Though, well, I have no feeling there. I don't know many.
Maybe there is a connection via HET, no? Then you have supersymmetric two-dimensional model which corresponds to supersymmetric HET. For example, this Chebyshev it's a rise in the semi-limited curve when you go to the mass deformation when you go to 1.
Well, I think, thanks. I think it's a good remark, but it's, well, it's more. Now you say about supersymmetric four-dimensional theory and not supersymmetric two-dimensional. But here, they are always, at least the example we discussed with Maxim, all theories are two-dimensional. But sometimes they are, say, getting from topological twist of n equal 2, which is rather natural. Sometimes by some other definition. When, say, you write down like BC plus beta gamma system, we saw recently in huge matrix form, but here in simple form. It's in a sense also supersymmetric. But, you know, here, one of the difficulties is that these theories are often oversimplified, and that's why you cannot catch them. But on the other hand, you can attain a lot. So you are daring to get here some full quantum answers. As you know, that was a story.
I understand my confusion that whenever I see the formula like this, I would say there is some Carnot rings,
Yeah.
and then it should be a supersymmetry.
Yeah, but what, for example, here there is this ground ring of two-dimensional gravity, which probably can have some supersymmetric description. But originally, it appears not from a supersymmetric theory. It's a very good point, yeah. That these rings, absolutely, they're often, and I don't really know any good reason, I cannot answer why they show up here. Just we know that, well, if we believe to Witten, people like him.
Sorry, so this, the way it works for non-rational B in this last part is that Chebyshev polynomials are are cosine of cosine n times
Yeah.
vice versa.
Yeah.
Cosine of n times
Yeah.
cosine.
Yeah.
And then you like just put this.
Yeah. Absolutely, Igor. So you just say that Tn of cos theta is cos n theta.
Yeah.
And you basically forget about the fact that at something integer or rational this is polynomial, but just use this cosine sine formulas. Absolutely.
B instead of n.
Yeah. Though I don't know any reason for doing that. And that's, since I started with, whenever you have all these polynomials and curves of finite genus, you have some points to base on, but in general, I don't know.
And probably in the talk, I have that v equals to 0, a limit should correspond to something like a GT. And the question is it true that
GT, you means this, not AGT, but this GT, yeah? Which I don't know what it is, yeah. Yeah, Jackie,
so is it true that this spectral curve reduces to the GT spectral curve? Because I don't remember precisely. Was the square and cosine of z or not?
well, you will tell me after the break, because as I told you, I don't know what is GT. So, yeah, well, you see, they write down many formulas. Some of them are very ugly, like spectral densities for certain matrix models. But some of them you can work with, like here, yeah, with these x's and y's. But, well, it's indeed nice because I really don't remember what is GT, but they do refer to GT in any case. They say like it, maybe in some limit, but that this is one more approach which should give the same results. But excuse me, I don't know.
Another question. So the median of this n was a product of two structure constants from which
Yes.
you can dually with.
Yes.
And in the minimal gravity, there were zeros or ones. Is the phenomenon the product of the structure constants in that case can be either 0 or 1 or
I think so. But I'm afraid that it depends on definition. Because there are two possible definitions, to my knowledge. And if you first take the product of structure constant, you get out of the minimality. But if you say that, no, let's fix it to be minimal and then take the product of structure constant, then you get this phenomenon that they're either 0 to 1, at least for these two k plus 1 case.
Any more questions? Okay, let's